Hey guys, tonight we travel back to a time before oceans, before continents, before moonlight touched the sea, to a universe where the Earth you know did not yet exist, and the sky above it had not even been invented. Picture darkness filled with a faint, ghostly glow, a wide, cold cloud of gas and dust drifting through space, so quietly it almost seems harmless, which is usually how the biggest cosmic dramas begin. Before you get cozy, take a moment to like the video and subscribe, but only if you genuinely enjoy spending time here with me. And if you feel like it, post your location and local time in the comments, because I always love seeing where in the world you're listening from while we wander through these sleepy little catastrophes of deep time. Let the world slow down for a moment. Let the fan murmur softly nearby, and let's slip into tonight's journey together. You are floating in a place that does not look important yet. There is no earth beneath you, no moon overhead, no blue marble glowing in the dark like the favorite child of astronomy posters. There is only a giant cloud, stretched across an enormous region of space, made of hydrogen, helium, and a sprinkling of heavier elements left behind by older stars that lived hard and died dramatically. Space has a talent for recycling. It never throws anything away. It crushes, melts, tears apart, and then calmly uses the wreckage for future projects. Very efficient, very rude. Somewhere in this cloud, something changes. Maybe a nearby star explodes. Maybe a shock wave ripples through the gas. Maybe gravity, patient as ever, simply notices a slight imbalance and begins leaning on it. That is how so many great things begin in the universe, not with a trumpet blast, but with a gentle loss of balance. One region of the cloud becomes just a little denser than the rest. Then that denser patch pulls in more material, then more, then more. Gravity does not need to hurry. It has all the time in existence, which gives it a certain confidence. As the cloud starts to collapse inward, it also begins to spin. This is one of those lovely cosmic details that feels almost unfairly elegant. Pull a cloud inward and its rotation speeds up, just as a skater spins faster when drawing in their arms. Suddenly, this sleepy drifting cloud is flattening into a vast spinning disk. At the center, material piles up into a growing protostar, the future sun, while around it stretches a broad disk of dust and gas, warm in some places, cold in others, chaotic but not random. This is the workshop where worlds will be made. The young sun is not shining the way it will later. It is still gathering mass, still compressing under its own gravity, still heating up. The center grows denser and hotter. Around it, tiny grains of dust begin colliding. At first, they are almost absurdly small, more like smoke than stone, fine particles drifting through the disk. They bump into one another and sometimes stick. It sounds unimpressive, and honestly, if someone described the birth of a planet as small dusty bits bonking together for a while, they would not be entirely wrong, just spectacularly underselling the result. Those grains become clumps, the clumps become pebbles, the pebbles become rocks. The rocks become larger bodies because once you have something with a little mass, gravity steps in and starts making introductions. Space, which had looked empty and wide, becomes crowded with ambition. Everywhere in the disk, material is gathering into lumps, and those lumps are crashing into one another. Some collisions shatter, some merge, some glance off, some change everything. Closer to the center, where the heat is stronger, lighter, volatile materials cannot easily survive. Water, methane, ammonia, those kinds of compounds do better farther out in the colder reaches. Near the sun, only tougher materials can hold their form. Metal, silicate rock, the ingredients for the inner planets. Mercury, Venus, Earth, Mars all begin in this hotter region as accumulations of mineral grit and metallic debris. You are watching the beginning of a sorting process that will shape the architecture of the solar system. It is less like a peaceful garden and more like a construction yard run by gravity, fire, and repeated acts of violence. As these growing bodies move through the disk, they sweep up smaller material along their paths. Their gravity helps them pull in more matter, which helps them grow bigger, which strengthens their gravity, which helps them pull in even more. It becomes a runaway process. Tiny advantages become enormous ones. In the modern world, this is called success. In planetary science, it is called accretion. Same basic mood, fewer motivational podcasts. One of these growing worlds is the early Earth, though at this stage you would never call it home. It begins as a protoplanet, a gathering of hot rock and metal forming through endless impacts. Each collision adds mass, and each impact releases energy. The energy has to go somewhere, and much of it becomes heat. So the larger Earth grows, the hotter it gets. Radioactive elements inside it also decay and add more heat. The pressure of accumulating material adds still more. Before long, this young planet is not a calm sphere of stone. It is a blazing, battered, partially molten world, still under construction and taking hits from every direction. And all around it, the solar system is still wild. There is no neat arrangement yet, no serene orbital ballet worthy of a museum mobile. There are countless leftover planetesimals, chunks of rock and metal ranging from mountain size to moonlet size, crossing paths, colliding, breaking apart, merging. The young Earth is being assembled in a cosmic shooting gallery. Each impact leaves its mark. Some merely add surface scars. Others plunge deep, delivering fresh material and stirring the interior. Many are big enough to melt wide regions of the planet's outer layers. The Earth, in its infancy, is less a finished object than a process. The young sun finally ignites in earnest as hydrogen fusion begins in its core. Light floods the solar system. Solar wind pushes away much of the remaining gas from the disk. The age of vague, cloudy beginnings starts giving way to something sharper, brighter, and more defined. The planets are still forming, but the stage lights are now on. The Earth circles this young star faster than it does today, in an orbit that is still stabilizing, while its surface glows with heat from within and punishment from above. If you could stand near it, which would be a very brief and deeply regrettable career move, you would see a world with no blue oceans, no white clouds, no green life, no quiet beaches for inspirational documentaries. You would see red and black rock, molten regions, constant impacts, plumes of ejecta rising into space, and a horizon blurred by heat. This is the Earth before gentleness, before the first raindrop, before the first tide, before the moon. Yet something recognizably Earth-like is already beginning to exist beneath the chaos. With every collision, the planet grows more massive, and that greater mass means stronger gravity, strong enough to hold onto more material, strong enough to shape itself into a sphere, strong enough, eventually, to separate its own insides by weight. But that deeper sorting has not fully happened yet. Right now, the Earth is still mixing itself through heat and violence, still becoming. It is a planet with a future, though nothing about it looks reassuring. And this is what makes the story beautiful. The world you know, with forests, tides, winter moons, and sleepy midnight skylines, begins in a place that seems completely unfit for beauty. It begins in dust, in impact, in fire, in collapse. It begins in a spinning disk around a young star that has only just switched on. It begins with matter learning how to gather itself into something larger, something heavier, something capable of holding a sky, then an ocean, then life, then a creature like you who can lie in bed millions of years later and wonder how all this happened in the first place. For a long while, the answer is simple. The Earth is formed because the solar system refuses to stay loose and scattered. Gravity keeps drawing things together. Heat keeps changing them. Motion keeps smashing them into new shapes. The early Earth grows by surviving collisions and by absorbing them, taking one blow after another until the blows themselves become the thing that builds it. It is being forged rather than assembled, and that distinction matters. Assembly sounds organized. Forging sounds honest. And somewhere ahead, still hidden in the dark distance of this story, one collision will matter more than all the others. One impact will not merely add to the Earth. It will tear part of it away, remake the sky, and give this young planet the companion that will shape its tides, steady its tilt, and haunt its nights forever. The young sun brightens at the center of everything, no longer just a swelling knot of collapsing gas, but a real star with enough force in its core to fuse hydrogen into helium and flood the newborn solar system with light. That light does not fall on peaceful planets lined up neatly in their lanes like polite little schoolchildren. It shines on turbulence, on debris, on unfinished worlds elbowing their way into existence. The whole place still feels improvised, like the universe built the set 5 minutes before the audience arrived. Around the sun, the disk of leftover material keeps moving in countless paths. Dust has become rock, rock has become larger bodies, and those larger bodies are still crashing into one another with very little concern for anyone's future coastlines. Earth is one of the winners in this violent contest, though winner here means a growing ball of molten damage. It is collecting mass quickly enough to become one of the dominant rocky planets in the inner solar system. That matters because size changes everything. A larger body has stronger gravity. Stronger gravity pulls in more material. More incoming material means more impacts, more heat, and more rapid change. The young Earth is becoming harder to ignore. If you could watch it over millions of years, sped up just enough to keep you awake but slow enough to enjoy the drama, you would see a world taking shape through repeated collisions. Some incoming objects are small, barely more than cosmic gravel. Others are colossal, the size of mountain ranges, small moons, even larger. Each strike releases tremendous energy. Rock melts, surface layers churn, debris blasts outward, then falls back again. The planet never really gets a chance to cool for long. It is like trying to bake a loaf of bread, while other people keep throwing bricks into the oven. This is also the age when the inner solar system begins to clear itself out. There had once been far more material crowding these orbits, but the larger protoplanets have started taking over. They pull in nearby debris, scatter some of it away, and crash into the rest. Earth is doing exactly that. Its neighborhood is still dangerous, but it is less a random cloud now and more a place where a few growing worlds are asserting control. The broad outline of the solar system is beginning to emerge from the earlier mess. The heat inside Earth becomes impossible to ignore. Some of it comes from the sheer violence of impacts. Some of it comes from compression, because as more material piles onto the planet, the pressure inside increases. Some of it comes from radioactive decay, with unstable isotopes quietly breaking apart and releasing energy inside the young world. All these heat sources work together until much of Earth becomes molten, or at least soft and mobile enough to behave like an almost liquid planet. This is not a solid sphere with a few lava lakes on top. This is a globe whose interior is still trying to settle while half of it glows. And when a planet is that hot, it begins to sort itself. Not calmly, not in a tidy classroom demonstration with colored sand in a jar, but in a vast, churning, planetary-scale separation driven by density. Heavy materials start sinking inward. Iron and nickel, abundant in the young Earth, do not want to stay mixed forever with lighter silicate rock. In a molten world, they can move, so they do. Slowly in human terms, quickly in planetary ones, dense metal descends toward the center. This is one of the most important transitions in Earth's history, even if it sounds, at first glance, like the sort of thing only geologists say at parties when they want the room to thin out. As the heavy metals sink, Earth begins to form a core. A metallic heart develops deep below the surface, first liquid, then with a solid inner portion much later. Around it remains a mantle made mostly of silicate rock, still hot, still mobile, still capable of slow convective motion. Above that, over time, a crust will emerge, fragile and thin compared with everything beneath it. The basic layered structure of Earth is being established, while the planet is still young enough to be regularly punched in the face by space rocks. That sinking metal releases even more heat. So differentiation, the process of Earth separating into layers, is not just a consequence of the planet being hot. It also helps keep the planet hot. The more the interior reorganizes, the more energy it releases, and the more molten the Earth remains. This is a world feeding its own transformation. The surface during this era would look almost unrecognizable. Huge regions may have been oceans of magma, glowing red-orange under a dark and dirty sky. There is no breathable atmosphere, no cloud deck drifting over peaceful water, No birds making inconveniently cheerful noises at dawn. Gases are being released from the interior through volcanic outgassing. Water vapor, carbon dioxide, nitrogen, sulfur compounds, and other gases escape upward from the hot mantle and crust. Some of these will matter enormously later. Right now, they mostly help make the place feel deeply unwelcoming. The earliest atmosphere of Earth is not the one you breathe today. Oxygen is almost nowhere in sight as a free gas. That comes much later, after life itself starts doing outrageous chemistry. The first atmosphere, if Earth briefly held one from the solar nebula, was likely stripped away early by solar wind and intense heating. What replaces it is a secondary atmosphere built from the planet's own interior. Volcanoes and molten rock exhale it into being. It is thick, unstable, and probably rich in gases that would make a modern travel brochure read like a threat. Even so, the presence of an atmosphere changes things. It begins trapping heat. It begins shaping how the surface cools. It creates a boundary between the violence of space and the violence of Earth, which is progress of a sort. Tiny dust grains and impact ejecta interact with these gases. Heat radiates outward. Surface layers harden, then melt again, then harden once more. The crust may form in patches, break apart, sink, and reform. The young planet behaves less like a finished object and more like an argument between fire and gravity. All the while, the sun continues to mature. Its fierce early radiation and solar wind help sweep away much of the remaining gas in the inner solar system. That matters for Earth because it confirms its identity as a rocky world rather than a gas giant core that never got the chance to bulk up. Out near Jupiter and Saturn, the story is different. There, the colder environment allows ices to survive, and the forming giants gather enormous atmospheres. Here, close to the sun, Earth remains a denser, smaller planet made of stone and metal. Harsh neighborhood, sturdy construction. There is something quietly elegant about this stage of the story. Earth is becoming distinct. It is no longer just one more anonymous clump in a dusty disk. It has mass, gravity, structure, and a future interior engine. The magnetic field that will one day protect the surface is not fully established yet, at least not in the way you would recognize, but the metal core being assembled will eventually make that possible. The tectonic restlessness that will one day move continents has its roots here too, in the hot mantle and the energy trapped inside the planet from its birth. Even the air and oceans of the future depend on this fiery beginning. A cooler, quieter birth would have made a very different world. Still, calm has not arrived. Earth is larger now, yes. More organized inside, yes. But the solar system is not finished with it. The region remains crowded with other protoplanets and massive leftovers from formation. Their orbits are not yet perfectly stable. They perturb one another, cross paths, and occasionally meet in impacts that can rewrite everything in a single afternoon of cosmic bad luck. Among those roaming worlds is one body that matters more than all the others. Not a random asteroid, not a passing fragment, a real planetary object large enough to have its own history, its own internal structure, its own destiny for a while. It moves through the inner solar system on a path that will one day intersect Earth's. The collision is still ahead, but the stage is being set. Earth is hot, layered, growing, and vulnerable. The other world is coming closer, whether either of them has a vote in the matter or not, which, to be fair, they do not. By the end of this era, the Earth already carries the bones of the planet you know. Core below, mantle above, crust trying to survive at the surface, gases gathering overhead, heat trapped inside, gravity strong enough to hold the whole thing together. It is still brutal, still glowing in places, still struck often enough to keep any decent real estate developer away, but it has crossed an invisible line. It is no longer just forming, it has become a world. And it is about to be hit hard enough to change its sky forever. That future is still hidden for a little while, because first the young Earth has to go on being young Earth, which means heat, motion, and a frankly unreasonable number of impacts. Its surface is trying to become solid, but the planet keeps getting interrupted. Crust forms in places, thin and dark and brittle, and then fresh collisions crack it, bury it, or melt it back into glowing rock. It is the kind of world that cannot sit still long enough to finish a thought. If you could look down from space, you would not see anything as gentle as continents. You would see a restless sphere marked by fire, shock, and constant rebuilding. Inside, the planet is more organized than before, but not settled. The core continues to define itself deep below, dense and metallic, while the mantle above it circulates with slow, immense movement. Hot material rises, cooler material sinks, and the whole interior behaves like a thick, planetary engine still warming up. Even at this early stage, Earth is becoming dynamic from the inside out. It is not a dead lump of rock. It is a body with an interior life. That matters because the surface depends on the deep interior in ways that are easy to miss when you are standing on a perfectly ordinary sidewalk, wondering why your phone battery is already at 30%. Volcanoes, crust formation, atmosphere building, later tectonics, all of it traces back to the heat trapped within the planet. The Earth is born hot and stays active because that heat does not simply vanish. It moves, escapes, reshapes, and drives change for billions of years. The sky above this early world would be thick with gases released from the interior. Water vapor is one of the most important. Even though the surface is still far too hot for stable oceans, water is already entering the system through volcanic outgassing, and likely through impacts from water-bearing bodies arriving from farther out in the solar system. The story of Earth's water is not a single neat delivery. It is more like a long, messy accumulation, a blend of sources arriving over time. Some is born from the planet's own interior chemistry. Some may come from asteroids rich in hydrated minerals. It gathers in the atmosphere first, waiting for a cooler future. Carbon dioxide and nitrogen also build up. Sulfur gases drift through the air. The atmosphere is dense, hazy, and nothing you would ever describe as refreshing. Sunlight filters through a turbulent veil over a hot and fractured surface. If there are moments when the crust cools enough to harden broadly, they do not last in peace. Impact after impact keeps punctuating the process. The planet is trying to become more stable, but the solar system is still in its rough years. And the rough years are not small. These are not occasional pebbles tapping the windshield. These are world-shaping collisions with objects large enough to alter the planet's rotation, change its chemistry, and reset huge portions of the surface. Every major impact dumps energy into Earth. Everyone churns the outer layers, excavates deep material, and hurls debris across the globe and sometimes into space. Some collisions bring new metals, some bring volatiles. Some simply bring destruction with no redeeming little gift basket attached. It is strange, really, how much of Earth's future depends on enduring this punishment. A world that forms too slowly may never grow enough to keep its atmosphere. A world that forms too gently may not separate into layers as efficiently. A world that avoids giant impacts altogether might never acquire the moon in the way Earth did. Violence is not a side note in this story. It is one of the main tools. As the impacts continue, Earth's spin is also changing. Every incoming object carries momentum. Depending on the angle and speed of a collision, it can speed the planet up, slow it down, tilt it slightly, or alter the orientation of its axis. The Earth you know, with its familiar day length and seasons, has not settled into those patterns yet. The young planet may be spinning faster than today, with shorter days, a hotter surface, and a more chaotic rhythm. Time itself would feel different here, not that anyone is around to complain about the schedule. The crust, when it does survive for a while, is likely more mafic than much of modern continental crust, darker and denser, more like the rocks beneath today's ocean floors. True continents in the familiar sense have not yet assembled. There are no old mountain ranges, no stable cratons stretching across quiet landscapes, no deep soils waiting for forests. The surface is more primitive, a skin still learning how to remain attached to the body beneath it. You can imagine standing there for a moment, safely impossible, looking across an expanse of hardening volcanic rock with glowing fractures in the distance. The horizon flickers with eruptions. the air is thick. The ground trembles from forces far below. Above, the sky is dimmed by gases and dust. And then, perhaps without warning, a distant light appears where no star should be, growing brighter, larger, more definite, until the sky itself seems to lean toward impact. This is the mood of the Hadean Earth, named after the underworld for reasons that feel, if anything, a little restrained. Yet even in this harshness, the planet is becoming more capable. The layered interior is a major step toward long-term geological activity. The atmosphere, however hostile, is the beginning of climatic regulation. Water vapor in the sky hints at future oceans. Cooling crust hints at future stability. Nothing here is ready for life, but some of the prerequisites are quietly falling into place. Earth is turning from a simple product of accretion into a complex system. Elsewhere nearby, other protoplanets are also moving through the inner solar system. Mars is taking shape. Venus is forming its own furnace of a future. Smaller bodies are being cleared away or folded into larger ones. But one of these neighboring worlds, a body about the size of Mars or perhaps a bit smaller, remains especially important. In modern retellings, it is often given the name Theia, after a Titaness in Greek mythology. The name is convenient, a little dramatic, and far more graceful than calling it that one catastrophic object headed toward Earth on a highly consequential orbital path, which admittedly lacks poetry. Theia is not a random intruder from the dark outer system. It likely forms in the same general neighborhood as Earth, from similar materials, as one more major protoplanet in the crowded inner solar system. That similarity will matter later when scientists study the Moon's composition and realize it looks uncannily like Earth in ways that suggest a shared origin. For now, though, Theia is simply another unfinished world moving through a gravitationally unstable region, where near misses and orbital resonances can gradually turn into disaster. Its path shifts over time. Gravitational interactions with other bodies nudge it. Earth's own growing mass helps shape the dynamics. Millions of years pass in this dangerous dance. Nothing in the solar system announces what is coming. There is no ominous soundtrack, no cosmic narrator clearing his throat. Just motion, gravity, and one orbit becoming a little less compatible with long-term peace. By this point, Earth has enough structure for the coming impact to matter in a very specific way. If the planet were still too small, the result would be different. If it had already cooled too much, different again. But the Earth is large, hot, partly molten, and differentiated enough that a giant collision can tear away outer material without simply shredding the entire planet beyond recognition. The conditions are almost absurdly precise in hindsight. Catastrophic, yes, but productive catastrophe, which sounds like the kind of phrase invented by someone trying to justify a truly terrible week. The world turns under its thick sky, molten in places, solid in others, carrying inside it the metals and minerals that will one day form mountains, magnetic fields, ocean basins, and the stone under your feet. It is already becoming home, though it still looks nothing like one. Theia moves nearer through the dark, also built of rock and metal, also a child of the same star. Two young worlds approach each other in the leftover violence of planet formation, and the gap between them is shrinking. When they finally meet, Earth will lose something and gain something at the same time. The blow will be unimaginably destructive. It will melt rock, launch debris into orbit, alter Earth's spin, and reset the surface in fire. But it will also create the raw material for the Moon, and with the Moon will come tides, a steadier axis, slower days, and one of the deepest influences on Earth's long future. The sky is still empty of that companion for the moment, but not for long. The distance closes in silence. Earth keeps turning through its heavy atmosphere, glowing at the cracks, cooling in patches, then breaking open again under its own heat. Theia moves on its crossing path, another rocky world with its own core, mantle, and violent childhood, and neither of them has any graceful way out of what is coming. In human life, disaster sometimes sends a few warnings first. A sound in the engine, a strange smell in the walls, a suspicious email with 3 spelling mistakes and an urgent request. In planetary life, the warning is simply orbital mechanics. The path tightens, the timing works out, and then 2 worlds arrive at the same place at the same moment. The collision is not a head-on smash in the cartoon sense. It is more likely a glancing blow, but that phrasing can sound almost polite, and there is nothing polite about it. Theia strikes the young Earth at tremendous speed, probably several kilometers per second, carrying enough energy to melt vast regions of both bodies and throw enormous amounts of material into space. The impact comes at an angle that matters, too direct, and the outcome changes. Too shallow, and much less material stays bound to Earth. But this angle is brutal and strangely fruitful. It tears into the planet's outer layers and transforms the whole system in a matter of hours. Try to picture that moment without turning it into a loud action movie. The scale is too large for noise in any normal sense anyway. You would see the edge of Earth brighten with impact heat more intense than most things the human mind is built to imagine. Crust and mantle material flash into vapor. Molten rock surges outward. A plume of incandescent debris rises above the planet, not as a neat fountain but as a swelling, twisted mass of vaporized silicates, melted rock, shattered fragments, and metallic spray. Part of Theia's body is destroyed outright. Part of Earth's outer layers are blasted away. The sky, such as it is, ceases to be a boundary and becomes part of the wound. The energy involved is almost beyond ordinary language. This is not one continent ruined or one ocean boiled. This is planetary-scale reworking. The surface melts. Vast portions of the mantle are stirred violently. The interior is shocked and heated again. Earth may become, for a time, almost entirely enveloped in magma. It is reborn inside catastrophe. And yet the planet survives. That survival is one of the most astonishing details in the whole story. Earth is not shattered into useless fragments drifting forever through space. Its mass is large enough, and the impact geometry favorable enough, that the bulk of the planet remains gravitationally bound as one world. Damaged, melted, altered, spinning differently, yes. Gone, no. Theia, on the other hand, is effectively lost as an independent body. Its identity ends in the collision, though much of its substance does not disappear. It becomes part of Earth and part of the debris around Earth. In that sense, the future moon is born from both worlds, but mostly from their outer rocky layers rather than their metal cores. This detail matters because it helps explain something scientists long puzzled over. The moon is not loaded with iron in the way you might expect if it formed from a simple chunk of a whole planet. It is less dense than Earth and relatively poor in metallic core material. That makes sense if the debris that formed it came largely from the mantles and crusts of Earth and Theia, while most of the heavy metal stayed with Earth's core or sank back into the merged planet. The result is a world and a moon that are chemically linked, close kin born from fire, but not identical twins. Immediately after the impact, Earth is surrounded by a disk of material orbiting around it. Not a ring like Saturn's icy elegance. Nothing that tidy. This is a hot, dense, chaotic debris disk made of molten droplets, vaporized rock, shattered fragments, and streams of matter colliding and spreading around the equatorial region of the planet. Some debris has enough speed to escape entirely into solar orbit. Some falls back to Earth in a rain of incandescent ruin. Some remains in orbit, trapped within the gravitational reach of the wounded planet. Earth itself is spinning faster after the impact, likely with a much shorter day than today. The exact number depends on the details of the collision, but the post-impact Earth may complete a rotation in as little as 5 or 6 hours, perhaps somewhat longer in some models. A day on this newborn world is not a calm 24-hour cycle. It is a rapid spin under a brilliant, hellish sky, with the remains of the collision circling overhead. For a while, there may be no clear moon yet, only the disk. Imagine looking upward from the surface, if the atmosphere and heat even allow such a view, and seeing not one serene orb but a glowing arc or thick band of material sweeping around the planet. The sky would carry a wound that has not yet closed. Rocks and molten droplets collide within that disk, merge, break, and merge again. Gravity starts doing what gravity always does. It gathers. It sorts. It turns chaos into structure, though never gently and never quickly by human standards. The outer parts of the debris disk lie beyond a critical distance called the Roche limit. Inside that distance, tidal forces from Earth are too strong for loose material to clump into a stable moon. Outside it, aggregation becomes possible. This is where the future moon begins to take shape. Fragments collide and stick. Larger clumps sweep up smaller ones. Molten material cools as it orbits, though the process is uneven and violent. A moonlet forms, then grows, then absorbs more material, eventually becoming one dominant body. The moon is not carved from Earth like a neat slice from cake. It is assembled from the aftermath of an impact, piece by blazing piece. And because all of this happens close to Earth, the newborn moon begins its existence much nearer than the modern one. Astonishingly near, perhaps only a fraction of its current distance, looming huge in the sky if you could see it clearly. It would rise enormous above the horizon, much larger than the familiar moon of tonight, dominating the heavens with a presence almost absurdly intimate. The tides it raises later will be far stronger because of this closeness. The relationship between Earth and Moon begins in proximity and power. Meanwhile, Earth remains almost impossibly hot. The surface is still a magma ocean or close to it, and the impact has reset much of the cooling process. The atmosphere is thick with rock vapor, steam, carbon dioxide, and other gases released and stirred by the collision. There is no peaceful pause after the event, no cosmic nurse entering with a clipboard and suggesting rest. Recovery is itself another phase of violence. Debris continues falling back. The surface continues churning. Heat continues escaping through a dense, glowing atmosphere. Yet something fundamental has changed. Before the impact, Earth was one forming world among several. After it, Earth is the center of a new two-body system. The Moontabe is gathering overhead, and that companion will influence Earth from then on in ways so deep and so constant that it becomes hard to imagine our planet without it. The length of the day, the strength of tides, the stability of Earth's axial tilt, perhaps even long-term climate patterns and the conditions for life on shorelines, all will be touched by this partnership. You can almost feel the scale of the transition. A world that had no moon is becoming a world defined by one. A sky that knew only impact debris is preparing to host a permanent companion. The same collision that could have erased everything instead creates one of the most recognizable features of Earth's existence. And there is one more quiet consequence hidden inside the violence. The impact may help explain why Earth's core and spin end up the way they do, and why the planet avoids certain alternative fates. Too much tilt, too little tilt, too fast a spin, too little angular momentum. All of these factors matter over deep time. The giant impact does not solve every mystery cleanly, and scientists still debate details of the models. But the broad idea remains powerful because it fits so much of what we see. The moon's size, its composition, Earth's rotation, and the shared isotopic fingerprints that suggest these two worlds were born from the same ruined fire. The debris disk continues circling. The outer clumps continue growing. The merged Earth and Theia continue settling into one altered planet. And slowly, out of molten wreckage and orbital persistence, the moon begins to become real. The first true moon rises out of wreckage. Not all at once, and not with that soft silver calm you know from quiet nights and late walks and windows left cracked open in summer. This moon begins as a hot, raw thing, assembled from a disk of shattered worlds. Around Earth, the debris keeps circling, colliding, merging, heating, cooling, and colliding again. Larger clumps gain an advantage, because once a body has enough mass, gravity starts doing its old, irresistible work. It draws in nearby fragments. It clears space along its path. It becomes harder to ignore. Somewhere beyond the Roche limit, One growing body begins to dominate the rest, gathering matter until it becomes the newborn moon. It is almost impossible to overstate how different this moon would have looked from the one above you now. It would have been much closer to Earth, perhaps several times closer than today, hanging huge in the sky when the clouds and haze allowed a view. It may still have been partly molten, glowing faintly from the heat of its own formation. Its surface was not yet the gray, battered face you know. It was a young world with a magma ocean of its own, hot rock slowly cooling beneath the blackness of space. Earth had created a companion, and the companion was every bit as dramatic as the event that birthed it. The Earth below was still no paradise. The giant impact had reheated the planet on an enormous scale. Any earlier crust that had begun to stabilize was largely reset or buried beneath new molten layers. The atmosphere remained thick and violent, loaded with vaporized rock, steam, carbon dioxide, nitrogen, sulfur gases, and all the other ingredients of a deeply unpleasant forecast. The surface glowed in places. Magma seas stretched across large regions. Debris still rained down from orbit because not everything that had been flung outward stayed up there. Some of it came back, and it came back hot. This stage is sometimes imagined as a pause after catastrophe, but it was not much of a pause. It was a reorganization. The Earth-Moon system had been created, yes, but the system still needed to settle. Earth's spin was faster than it is now. The Moon orbited close and moved quickly across the sky. The gravitational pull between them was intense. Tidal forces began almost immediately to shape both bodies, especially Earth. Modern tides already move astonishing amounts of water. On the young Earth, with the Moon much closer, the effect would have been far stronger. Later, once liquid oceans formed, those tides would become extraordinary, but even before long-lasting oceans, the tidal pull mattered. It flexed the planet's outer layers. It stirred molten regions. It affected rotation and orbital energy. Earth and Moon had entered a long gravitational conversation, and from the very beginning it was a forceful one. The Moon raises a tidal bulge on Earth. Earth, spinning quickly, drags that bulge slightly ahead of the line connecting the two bodies. That offset matters. Gravity between the Moon and the bulge transfers angular momentum from Earth's rotation to the Moon's orbit. In plain terms, Earth gradually slows down and the Moon gradually moves farther away. This process is still happening today. The day gets longer by tiny amounts. The Moon recedes by a few centimeters each year. But in the early system, when everything was closer and more intense, the exchange happened more dramatically. So the Moon did not simply appear and stay where it was. It began close, then slowly started drifting outward. Earth's day, once perhaps only a handful of hours long, began the long stretch toward the 24-hour rhythm you live by now. The partnership between planet and Moon was not static. It evolved. The sky changed. The timing of dawn and dark changed. The tides changed. The whole system breathed outward into greater stability. Meanwhile, the Moon itself was changing fast. Like Earth, it likely had a global or near-global magma ocean early on. The outer layers slowly cooled. Minerals crystallized. Denser materials sank. Lighter ones floated upward, helping form the Moon's early crust. Bright highland regions probably formed from lighter minerals such as plagioclase floating atop the molten surface. The darker lava plains, the maria that are visible from Earth today, would come much later through volcanic flooding of giant impact basins. For now, the Moon was still a fresh body, bright and hot, and geologically simple compared with the Earth. There is something almost tender hidden inside all this violence. Earth had been struck hard enough to lose part of itself, and from that loss came a companion that would never fully leave. The Moon is made from Earth's history turned outward. A piece of the planet's own early story was lifted into the sky and set into orbit, where it could keep watch for billions of years. That sounds poetic because it is, but it also happens to be physically true, which is very satisfying and rare enough that we should enjoy it. As Earth slowly radiated heat into space, the upper atmosphere began to cool. Water vapor that had been trapped in the air would eventually condense once the surface temperature dropped enough. That transformation was still ahead, but the path toward it had begun. Steam-filled skies would one day produce unimaginable rains, not for an afternoon, not for a season, but over spans of time that defy ordinary weather language. The first oceans were waiting inside the atmosphere, patient and suspended. The crust also kept trying to establish itself. Thin solid layers formed over the magma below, broke, sank, and formed again. Some early crust may have survived in scattered fragments, though most of the visible record from this era has long since been erased by later tectonics and recycling. Earth is frustrating that way. It rarely keeps neat baby pictures. Much of its earliest history has been melted, buried, deformed, or swallowed by the mantle. The Moon, with far less geological activity, ends up preserving more of the ancient impact record than Earth does. So in a way, the Moon becomes not only Earth's companion, but also one of the best witnesses to the violence of the early solar system. Overhead, it loomed enormous. Imagine a moon so large in the sky that it feels almost too close, a presence rather than a decoration. It would have dominated the horizon, moved more quickly through the heavens, and driven tides with an intensity modern coastlines would find absurd. Nights, if the atmosphere ever cleared enough, would have been haunted by this giant newborn neighbor, glowing over a world still too hot for calm. And still the story keeps folding forward. Earth is cooling. The moon is moving outward. The day is lengthening. The atmosphere is thickening and changing. The surface is beginning the long struggle toward stability. For the first time, the foundations of the familiar Earth are starting to appear through all the fire. Not the finished planet, not even close, but the structure of its future. Because once the heat drops far enough, the steam will fall. Once the steam falls, oceans will gather. Once oceans gather, the moon's pull will write itself across water, shoreline, rhythm, and time. And then this story of rock and impact begins turning, very slowly, into a story that could someday hold life. The heat keeps leaking away, slowly enough to test anyone's patience, though patience is one thing deep time has in embarrassing abundance. Earth is still hot, still scarred, still restless from the giant impact, but the worst brilliance of that immediate aftermath begins to fade. The rock vapor in the atmosphere thins. The molten surface, while still widespread in places, no longer rules the whole planet without interruption. Solid crust forms more often and lasts longer. The young moon continues its slow retreat outward, though it remains dramatically close by modern standards, large enough to dominate the sky and powerful enough to keep tugging hard on the planet below. And then the air changes. For a very long time, water has been waiting above the planet as vapor, mixed into that thick early atmosphere from volcanic outgassing and from water delivered by impacts. It has hovered there because the surface has been too hot to hold stable liquid. But cooling eventually crosses a threshold. The upper atmosphere chills enough, then lower layers follow and water begins to condense. At first it may fall, flash to steam on contact, and rise again. Then it falls again, and again. Over time, the balance shifts. Rain no longer loses every battle with heat. This is one of the great quiet revolutions in Earth's history. No trumpet, no special effects package. Just the moment when the sky finally begins handing water to the surface faster than the surface can throw it back. Rain gathers in low places. Steam clouds roll across a dark, volcanic world. Water fills basins in crust that is still young and unstable. The first long-lasting bodies of liquid begin to exist. If you could stand there safely, which remains one of science fiction's worst ideas, you would see a world that still looks severe but is crossing into something new. Black rock, violent weather, heavy clouds, rain falling through hot air, lightning probably flashing through thick, chemically active skies, water rushing over fresh stone that has never known a river before. The planet is not peaceful yet, but it is no longer only fire. It is becoming a place where fire and water must share the stage, and that changes everything. These early oceans may not have looked blue in the way you picture them now. The atmosphere was different, the chemistry was different, and the sky itself may have been dimmed by haze and volcanic gases. But liquid water was there, pooling, circulating, reacting with rock, carving, dissolving, transporting minerals, turning the planet's surface into a more complicated and interesting system. Once water arrives in large amounts, geology becomes chemistry's favorite dance partner. Things start reacting everywhere. The crust keeps evolving under all of this. Earth's outer shell is still thinner and more active than later, and the mantle beneath it remains intensely hot. Early forms of crust are likely broken, mobile, and repeatedly recycled. Whether full modern-style plate tectonics begins immediately or develops more gradually is still debated, but what matters for the story is that the surface is not frozen in place. It moves, overturns, melts, and reforms. The planet is alive with internal motion. The oceans, once they spread widely enough, also become part of the cooling system. Water interacts with hot crust, absorbs heat, circulates through cracks, alters minerals, and helps regulate temperature at the surface. The atmosphere and oceans begin working together, rough and primitive though they are, as a climatic engine. Carbon dioxide dissolves into water. Chemical weathering begins pulling some gases out of the atmosphere and locking them into minerals. The long, slow balancing act between sky, sea, and stone begins here. And over all of it, the moon keeps pulling. The tides on this young Earth would have been tremendous. Because the moon was much closer, its gravitational grip was stronger, and if broad oceans already existed, then those waters would have surged and withdrawn with astonishing force. Coastlines, if they can even be called that yet, would have shifted under giant tidal ranges. Shallow seas might flood and empty over wide stretches of land or volcanic plain. Pools would fill, evaporate, refill, and mix with minerals from the rock. It is the sort of repeated, rhythmic upheaval that later scientists would stare at thoughtfully and wonder whether it helped prepare some of the chemical stages for life. The evidence is indirect, the debate is lively, but the possibility is delicious. Even if life is still far ahead, the Earth-Moon relationship is already shaping the conditions under which life will someday emerge. The moon is doing more than decorating the sky. It is affecting Earth's spin, its tides, the way energy moves through the system, and perhaps the long-term stability of the planet's tilt. That last point is especially important. Earth's axis is tilted, which gives you seasons. A planet's tilt can wobble over time under the gravitational influence of other bodies. The moon helps stabilize Earth's axial tilt, keeping the swings more moderate than they might otherwise be. Without the moon, Earth's climate history might have been much wilder, perhaps swinging through more dramatic shifts over long timescales. That stabilizing effect does not mean the moon showed up as a polite climate consultant, clipboard in hand, ready to optimize the biosphere. It simply means physics can be unexpectedly generous after being violently rude. The same collision that nearly remade Earth also gave it a companion that would help make the planet more stable across the ages. Deep time has a strange sense of irony. The sky during this era would still be alien. The sun was slightly dimmer than it is today, because young main sequence stars brighten gradually over time. That creates one of the fun scientific puzzles called the faint young sun paradox. If the sun was dimmer, why did Earth have liquid water so early? The likely answer is that greenhouse gases in the atmosphere, especially carbon dioxide and perhaps methane later on, helped trap enough heat to keep the oceans from freezing globally. So the early Earth may have lived under a dimmer sun, but a stronger atmospheric blanket. Not cozy, exactly, but effective. The moon itself continues cooling. Its magma ocean crystallizes further. A crust thickens. Large impacts from leftover debris still strike both Earth and moon, though Earth will erase much of that ancient record over time, while the moon keeps it etched on its face. This difference becomes profoundly useful much later when human beings begin studying craters and collecting lunar samples. The moon turns out to be something like a preserved archive of the solar system's rough youth, while Earth is the overachieving sibling who keeps renovating and throwing out all the old furniture. And through millions of years, the day lengthens. The young Earth that once spun through a day in perhaps just a few hours slows under the moon's tidal drag. Sunset takes longer to return. The frantic rhythm begins stretching into something roomier. This is one of the most intimate ways the moon changes Earth. It reaches down through gravity and literally reshapes time as experienced on the surface. Not time itself, of course. The universe is not handing out special exceptions, but the cadence of day and night, the pace of heating and cooling, the rhythm under which oceans, weather, and later biology unfold. So the world is no longer just surviving formation. It is entering a new condition. Oceans are gathering, crust is cycling. The atmosphere is interacting with sea and stone. The moon is established overhead, slowly receding, steadily pulling. Earth is becoming not merely a planet but a system, one in which the sky, the sea, the deep interior, and the neighboring moon all speak to one another through gravity, chemistry, and heat. And as that system strengthens, the next great test approaches, because the early solar system still has not completely calmed down. There are more impacts to come. Some of them will be among the largest since the moon-forming collision. The age of easy peace has not arrived yet. The Earth has water now, and a sky, and a moon, and the beginning of recognizable cycles. Which is, naturally, when the universe decides to keep throwing rocks at it. The rain has fallen, the first oceans have begun to gather, and the moon has taken its place in the sky, but the solar system is still in one of its bad moods. Leftover debris remains everywhere, from smaller planetesimals to large impactors crossing unstable paths. Earth has already survived the collision that gave it the moon, which feels like enough cosmic excitement for any reasonable planet. Yet reason has never been one of the strong points of early planetary history. The bombardment continues. You can imagine the surface during this age as a world caught between creation and interruption. Water spreads across low regions, collects in basins, and begins the long work of reacting with rock. At the same time, impacts keep arriving, some small enough to scar a region, others large enough to reset vast areas. The crust tries to hold and often fails. Oceans form, and in some places they may boil away locally under the force of a major strike, only to gather again later. Stability does not arrive all at once. It arrives in pieces, and each piece has to survive a universe that still enjoys throwing hardware around. This era is often associated with what scientists call the late heavy bombardment, though the timing and even the exact nature of that event are still debated. The broad idea is that the inner solar system endured a prolonged period of intense impacts long after the main planets had formed. Whether it came as a sharp spike or a drawn-out decline in violence, the message for Earth was the same. The sky was not done dropping trouble. The moon remembers this well. Its surface, with so little air, water, or tectonic recycling, preserves the marks of those ancient collisions in crater after crater, basin after basin. Earth almost certainly took similar hits, but its own geology erased much of the evidence. The moon, in that sense, becomes a record keeper. It is the quiet sibling with the better memory. When you look at the lunar face today, you are seeing a page that Earth once shared but later rewrote. Some of those impacts on Earth would have been astonishingly powerful. A large incoming body strikes, releases energy in an instant, excavates deep crust, melts rock, launches debris, shocks the atmosphere, and sends waves through the oceans. If the impact lands in water, enormous steam plumes rise. If it lands on crust, molten rock may spread across huge regions. Tsunami-like surges can race across early seas. The atmosphere changes temporarily. Dust and aerosols fill the sky. Yet Earth keeps recovering. It keeps cooling, cycling, and rebuilding. And this matters because every time the planet recovers, it does so with a little more resilience. More crust survives, more water remains, more long-term patterns can take hold. The bombardment does not prevent Earth from becoming a stable planet forever. It slows the process, bruises it, and complicates it, but the overall direction remains. The oceans come back. The crust reforms. The moon continues outward. The day continues to lengthen. Inside Earth, The mantle is still far hotter than today, driving vigorous convection. Heat escapes upward through volcanic activity, crustal recycling, and hydrothermal systems where water moves through hot rock and emerges chemically transformed. These environments may seem like minor technical footnotes at first, but they are among the most interesting places on the early Earth. Where water meets heat and mineral-rich rock, chemistry becomes lively. Elements dissolve, precipitate, react, and cycle. The planet begins building local environments with strong gradients of temperature and chemistry, the kind of environments that later discussions about the origin of life will circle back to again and again. Nothing alive may be here yet, or if the first stirrings have begun, the evidence is hidden deep in time. But the stage is improving. Oceans provide solvent and mobility. Volcanism provides heat and fresh minerals. Impacts, inconvenient as they are, also deliver materials and create temporary niches. Tides from the close moon continue flooding and draining coastlines and shallow basins. Earth is no longer merely a hot rock cooling in space. It is a chemically active world with cycles. The moon's influence becomes easier to appreciate here. Because it remains much closer than today, the tides are still vast. Shorelines advance and retreat over wide areas. Tidal currents are stronger. The exchange between sea and land, between shallow pools and deeper basins, happens with relentless rhythm. Even the rotation of the planet, still faster than modern Earth, combines with these tides to produce a very different daily experience. Days are shorter, nights return sooner, and the moon appears larger and more commanding above the water. There is a grandeur to this version of Earth that has nothing to do with comfort. Imagine dark volcanic islands rising from young seas beneath a sky layered with cloud and haze. Imagine the moon looming above them, enormous and bright through gaps in the atmosphere, its pull lifting the oceans into long, muscular tides. Imagine lightning over warm rain, steam rising where hot rock meets cold water, and distant impacts occasionally flashing on the horizon, like reminders that the solar system still has a temper. It is not a world made for people, but it is a world becoming capable of more than stone. The atmosphere continues changing as well. Carbon dioxide remains important, helping keep the young planet warm under a dimmer sun. Nitrogen builds the background bulk of the air. Water cycles between ocean and sky. Other gases from volcanism come and go in varying amounts. What is still missing in any major free form is oxygen. That absence defines the early atmosphere. There is no breathable air, no ozone shield like today's, no blue sky in the familiar sense. But the chemistry of the atmosphere, ocean, and crust is becoming more interconnected, more dynamic, and more able to support future change. Meanwhile, the moon cools into a more recognizable body. Its crust thickens. Its early magma ocean solidifies further. The giant basins formed by later impacts will eventually fill with dark volcanic lavas, creating the maria visible from Earth. But for now, the lunar surface is still mainly the ancient highlands and fresh scars of bombardment. Tidally, the moon is also evolving. Very early on, gravitational interaction with Earth slows the moon's own rotation until it becomes tidally locked, always showing the same face to Earth. That familiar one-sided gaze begins astonishingly early. From then on, Earth always sees one hemisphere, while the far side remains hidden until much later, when human machines finally go look. That tidally locked relationship adds to the intimacy of the Earth-Moon system. The moon is not just nearby. It is physically coupled to Earth in a deep dynamical way. One face turned homeward, one world slowing the other's spin, both moving together through space around the sun. Their partnership, born from a collision, becomes one of the defining structures of Earth's history. And through all of this, time keeps doing what it does best. Millions of years pass, then tens of millions. The rate of impacts gradually declines. Not to zero, not for a very long while, but enough that Earth starts holding on to its progress more reliably. Oceans deepen and spread. Crust survives longer. Weathering and erosion begin their endless patient work. Volcanic gases continue to feed the atmosphere, while water and rock continue to pull parts of that atmosphere back down into minerals and sediments. A balance, still rough and shifting, begins to emerge. This is when Earth starts feeling less like a temporary accident and more like a lasting planet. Not a calm one, not yet an inhabited one in any obvious way, but a lasting one. A world with a deep interior engine, a working hydrologic cycle, a massive moon shaping its tides and rotation, and a surface no longer entirely at the mercy of formation itself. Soon, the most dramatic acts of assembly will be behind it. The next great changes will come not from becoming a planet, but from becoming a place where something new can begin. The violence eases slowly, like a storm that forgets to leave all at once. Earth still takes impacts, of course. Space never becomes perfectly tidy, and the solar system never turns into a sealed museum display where nothing bumps into anything ever again. But the age of non-stop planetary abuse begins to loosen its grip. The largest bodies have mostly claimed their territory. Many of the leftover fragments have already been swallowed, scattered, or shattered. What remains is still dangerous, but no longer powerful enough to keep resetting the whole planet every few million years. That change matters more than almost anything. It means Earth finally gets time to keep becoming itself. The oceans now hold their ground. They are not just temporary puddles steaming off hot stone and vanishing again. They are broad, lasting bodies of water spread across much of the surface, deep enough to absorb heat, move chemicals, and shape the climate on a planetary scale. Rain falls, rivers likely form in some early fashion, water wears at rock, and the atmosphere and oceans begin acting less like two separate realms and more like parts of one system. The sky feeds the sea feeds the crust feeds the air. Earth is starting to behave like a living machine long before anything biological is there to admire the engineering. And above all of it, the moon keeps watch. It is still closer than the modern moon, still larger in the sky, though it has already begun that long retreat outward. It pulls at the oceans with enormous force. Tides rise and fall over distances that would make a modern coastline feel slightly melodramatic and underprepared. Water surges into shallow regions, then drains away again and again, on a planet whose day is still shorter than the one you know. The rhythm is faster, stronger, younger. The Earth-Moon partnership is no longer just a consequence of the ancient impact. It is one of the engines of the world. This partnership also reaches into the deep future in a quieter way. Earth's axial tilt, the slant of its spin axis relative to its orbit around the Sun, gives the planet seasons. That tilt is never perfectly fixed. Gravity from the Sun, Jupiter, and other bodies all nudge it over time. But the Moon acts like a stabilizing weight, limiting the wild swings that might otherwise make Earth's climate more chaotic over long stretches. Without the Moon, the tilt could wander more dramatically. Summers and winters might shift in much stranger ways over deep time. Climate zones might migrate more violently. Stability would be harder won. That does not mean the Moon made Earth magically perfect. It just means one ancient collision happened to produce a companion that made the planet steadier than it might have been, which, for a cosmic accident, is a remarkably thoughtful gesture. The crust continues to change as well. Early Earth was hotter inside than modern Earth, so the mantle convected more vigorously, and the outer shell may have behaved differently from the neat plate tectonics diagrams you remember from school. But over time, the basic pattern becomes more recognizable. Crust forms, moves, sinks, remelts, rises again. Denser oceanic material cycles downward more easily. More buoyant continental fragments, once they begin to emerge and survive, resist recycling better. Tiny ancestral pieces of continent may start appearing, not the giant landmasses of later ages, but seeds of them, rafts of lighter crust that float a little higher and last a little longer. That distinction is crucial. Earth does not just need oceans and atmosphere to become interesting. It also needs diversity on the surface. It needs shallow seas, volcanic arcs, mineral-rich coastlines, newly exposed rock, changing basins, and a moving crust that keeps refreshing the chemistry. A dead, uniform planet is geologically simple and biologically stingy. Earth is neither. It is becoming varied, restless, and chemically generous. The seafloor, especially, is a place of extraordinary activity. Hot water circulates through newly formed crust, emerges through vents, and carries dissolved minerals from the interior out into the ocean. These hydrothermal systems create sharp chemical gradients, places where energy is stored in difference, where hot meets cold, mineral-rich meets mineral-poor, reducing conditions meet oxidizing ones. These environments are among the most intriguing candidates for the earliest steps toward life, because life, in its simplest sense, is very good at exploiting gradients. It loves a slope. Give chemistry a persistent energy imbalance and enough time, and interesting things begin to happen. The exact path from non-living chemistry to the first living systems remains one of the greatest mysteries in science. No one gets to wrap it up neatly with a bow and say, yes, this was definitely the Tuesday afternoon when life officially started. But the early Earth of this period has many of the ingredients that make the mystery plausible. Liquid water, available elements, energy sources from sunlight, volcanism, and chemical disequilibrium, cycles of concentration and dilution, mineral surfaces that can help organize reactions, strong tides from the close moon, countless microenvironments where molecules can gather, break apart, and gather again. You can feel the story changing here. For so long it has been about matter assembling, heat escaping, worlds colliding, and surfaces cooling. Those things still matter, but now another possibility enters the room. The planet has become stable enough and complicated enough that chemistry is no longer just background detail. It may be preparing for something profound. Even without life, the atmosphere continues its long negotiation with the surface. Carbon dioxide dissolves into the oceans and reacts with rocks. Volcanic outgassing keeps replenishing gases from below. Weathering draws some of them down again. This carbon cycle, rough and early though it is, becomes one of Earth's great climate regulators. It helps prevent the planet from remaining too hot forever, and also helps keep it from freezing solid under the fainter young sun. Earth begins teaching itself balance. Not perfect balance, not stillness, but a workable, resilient kind. The moon's gradual retreat continues to reshape time. Days lengthen, tidal energy dissipates. The system loses some of its early intensity and gains a little more calm. The great tides do not vanish, but they become less extreme than in the moon's first close embrace. The sky slowly changes with that distance. The moon still looks large, still deeply present, but it is on a long path away from the world that made it, not leaving exactly, just stepping back, centimeter by centimeter, age by age. There is something almost emotional about that if you let yourself sit with it. Earth and moon begin in violent closeness, born from collision, joined in heat, their early relationship intense enough to reshape the planet's days and oceans. Then, over billions of years, they remain bound while slowly widening the space between them, still connected, still influencing each other, just no longer as overwhelmingly close. A very cosmic version of learning healthy boundaries. By now the young Earth would look, from far away, more familiar than alien. Dark oceanic expanses, cloud systems moving across the atmosphere, volcanic landmasses breaking the surface here and there, a substantial moon overhead. Still no forests, no animals, no oxygen-rich air, nothing you would mistake for the modern world, but unmistakably a real planet, mature enough to carry long-term history. And that is the key change. Earth is no longer simply forming, it is ready to begin transforming. The next part of the story belongs to what this planet does with its stability, its oceans, its chemistry, and its moonlit tides. Because once a world becomes this active, this varied, and this persistent, the door opens to the smallest revolution of all. And the smallest revolutions, as it turns out, are the ones that change everything. The smallest revolutions do not announce themselves with fire. That is almost funny after everything that came before. Earth was built in collision, melted in impact, sorted by gravity, drenched in steam, and shaped by tides so immense they must have seemed like the planet breathing too hard. The moon arrived in catastrophe. The oceans arrived in rain beyond any reasonable weather report. The crust rose, broke, sank, and rose again. For hundreds of millions of years, the story was loud in every possible geological way. And then, somewhere in that restless world, the next great change began quietly. Not visible from orbit, not dramatic from a mountaintop, not something the moon could admire from above. Just chemistry finding a way to persist. No one knows the exact place. No one can point to one perfect shore, one hydrothermal vent, one tidal flat, one warm little pool and say with total confidence, yes, right there, that was the first moment. The early Earth kept no neat diary, and the oldest rocks have been reheated, folded, buried, and recycled so many times that much of the first evidence is gone, but the conditions were there. Water, energy, carbon, nitrogen, sulfur, phosphorus, metals, mineral surfaces. Repeating cycles, time, enormous, generous amounts of time. That is what makes this phase so beautiful. The Earth and Moon story is no longer just about whether a planet can survive formation. It is about whether a formed planet can hold onto enough stability for complexity to grow. Oceans provide solvent. Volcanoes and vents provide chemical energy. The atmosphere provides gases that can dissolve, react, and circulate. Tides stir coastlines, mix shallow pools, and rhythmically concentrate and dilute dissolved compounds. The crust keeps supplying fresh minerals. The moon keeps pulling. The sun keeps rising on a world that has stopped merely enduring and started experimenting. Imagine one of those coastlines, not a beach in any modern sense. No dunes, no gulls, no footprints, no children losing sandals in wet sand. Just rock, water, minerals, heat, and the constant pulse of tides under a much closer moon. Pools fill, then partly evaporate, then refill. Dissolved compounds become more concentrated, then spread again. Clays and mineral surfaces offer places for molecules to gather and align. Elsewhere, deeper in the oceans, hot water rises through cracks in the crust, carrying dissolved metals and reduced chemicals, meeting colder seawater and setting up steep gradients in temperature and chemistry. Those gradients matter. Life, at its most basic, is a master of stealing useful energy from differences. If one side is richer in electrons, or hotter, or more acidic, or more chemically eager than the other, then a pathway may exist. Early Earth was full of such unevenness. It was not chemically bland. It was alive with imbalance, and imbalance is opportunity wearing a lab coat. You do not need to imagine anything as tidy as modern cells appearing overnight, because that is not how any of this would have worked. The road from simple chemistry to the first true life must have involved countless dead ends. Molecules forming, breaking apart, reforming. Networks that almost worked. Structures that held briefly, then failed. Reactions that became self-reinforcing in one environment and impossible in another. It was probably messy, local, fragile, and unbelievably slow. Which is to say, a very Earth-like innovation. At some point, though, chemistry crossed a threshold. Molecules or networks of molecules began doing something extraordinary. They did not just react, they persisted. They copied with variation, however crudely. They exploited energy flows. They occupied niches and continued. Once that happened, even in the simplest form, Earth stopped being only a geophysical story. It became a biological one. The oldest signs of life are still difficult, debated, and often frustratingly subtle. Ancient isotopic signatures in very old rocks hint that life may have emerged surprisingly early, perhaps not long after the worst bombardment eased. Some ancient structures called stromatolites, layered formations associated with microbial communities, appear later in the record as more visible testimony. But for this sleepy journey, what matters is the broader truth. Earth became habitable early, and perhaps inhabited early too. That is astonishing. A planet born in fire, struck into a moon-bearing system by catastrophe, cooled under a dim sun, drenched in violent rain, and harassed by impacts still managed to become the only world we know where stone gave way to biology. And the moon is in that story too. Not because moonlight itself created life, not because lunar romance seeped into the oceans and made microbes feel poetic, though that would make for a very bold scientific paper. The moon mattered because it had already shaped the conditions under which Earth stabilized. It helped slow the spin. It raised the tides. It may have helped moderate axial chaos. It created rhythmic coastal environments unlike those of a moonless Earth. Even if life could have emerged without it, the moon became part of the environmental framework in which Earth's chemistry learned how to keep going. Over time, the planet's systems grew more interwoven. The interior still drove volcanism and recycling. The oceans still moved heat and dissolved minerals around the globe. The atmosphere still responded to outgassing, weathering, and eventually life itself. Early microorganisms, once they existed, did not merely sit passively on the surface. They began altering the chemistry of the world around them. That effect was small at first, almost laughably small against the scale of ocean and stone, but small things with enough time become geological. For a long stretch, the atmosphere remained low in free oxygen. The earliest life likely made its living without it. Oxygen would rise much later through the work of photosynthetic organisms, and when it did, it would transform the planet in one of the deepest chemical revolutions in Earth history. But even before that, life had already become part of the Earth system. The planet and its inhabitants began changing one another. And through every age, the moon remained overhead, receding slowly, never leaving, its face turned earthward in permanent tidal lock. It watched the oceans it helped stir. It watched impacts fade in frequency. It watched crust recycle and continents begin their first uncertain careers. It watched the first living films and mats spread through shallow waters, utterly unaware, one assumes, of how much future poetry and insomnia it would inspire. From far away, the Earth would now look more and more like a world you could recognize. Oceans broad and dark, clouds moving in organized systems, volcanic landmasses, perhaps the first persistent continental nuclei, and a moon, still larger than today but no longer the enormous presence of its earliest closeness, hanging above a planet that had crossed from formation into history. That crossing is the true wonder here. Earth did not remain a molten accident. It did not become a sterile rock circling the sun in silence. It became dynamic, wet, layered, tidal, and alive. And the moon did not remain a cloud of debris or fall back into the world that made it. It became a lasting partner, one that still shapes the Earth in subtle ways every day. Together, they became a system with memory. Because every tide today remembers that ancient closeness. Every long, steady day remembers when the planet spun much faster. Every eclipse remembers the geometry born from impact. Every glance upward at the moon remembers a time when it was made of fire and ruin and newly gathered stone. And every living thing on Earth, including the one listening to this right now, belongs to a world whose earliest history had to go exactly this strangely, violently, beautifully right. And that is the part that stays with you, long after the molten oceans and impact plumes and roaring rains have passed from the mind like a dream you were almost sure you would remember in the morning. You began in a cold cloud of dust and gas, drifting through a dark stretch of space with no Earth, no moon, no sky, no sea, no night worth naming. Gravity gathered that cloud inward. The young sun ignited. Dust became stone, stone became worlds, and one of those worlds, through repeated collisions and an almost absurd amount of heat, became Earth. Not the Earth of forests and coastlines and sleeping cities, but a fierce early version of it, glowing, broken, reforming, learning its own shape through violence. Heavy iron sank deep and built the core. Lighter rock rose and made mantle and crust. Volcanoes exhaled the first real atmosphere. Water waited in the sky. Then came the blow that could have ended everything before anything had even begun. A young world, Theia, crossed Earth's path and struck it with enough force to remake the planet's surface and throw a ring of molten wreckage into orbit. Out of that ring, the moon began to gather, not placed gently in the sky, not arriving as some decorative extra, but born from the same catastrophe that nearly erased the growing Earth. A companion made from fire and fragments. A second world pulled from the raw edge of disaster. That moon rose huge above the early planet, close enough to dominate the sky, powerful enough to drag at the oceans that had not even fully formed yet. It slowed Earth's spin. It stretched the days longer. It pulled at the crust, then later at the seas, shaping tides of astonishing force. It helped steady the planet's tilt. It became part of the machinery of Earth, part of the timing, part of the rhythm, part of the reason the world could settle into something stable enough to carry a longer story. And Earth did settle, though never all at once. The air cooled, steam condensed, rain fell through that strange early sky until water could remain on the surface and collect into oceans. The crust hardened, broke, sank, and rose again. Impacts kept coming for a long while because the solar system was still clearing its throat with all the subtlety of a demolition crew, but the pace slowly eased. The ocean stayed. The moon drifted outward. The planet began holding onto its progress. That may be the most comforting truth in the whole story. Earth was not made in peace. It was made in chaos and then slowly, stubbornly, turned itself into a place where calm could exist. A place where chemistry could become more complicated. A place where tides could move across real shorelines. A place where cycles of water, rock, atmosphere, and heat could keep working together for ages beyond counting. A place where the smallest kinds of persistence, fragile at first, could begin to matter. At some point, the chemistry crossed into life, quietly. No dramatic spotlight from the heavens. No neat dividing line in the rocks saying life starts here. Just the long work of a planet that had become stable enough, wet enough, active enough, and strange enough for matter to begin organizing itself in a new way. Molecules learned how to keep going, then how to copy, then how to change. And after that, the story was never only geological again. Everything that came later depended on those early acts of formation. The core still turns beneath your feet. The mantle still moves. The crust still drifts. The oceans still answer to the moon. The day you live inside is longer because the moon has been gently stealing a little of Earth's spin for billions of years. The seasons remain relatively steady because that same moon helps calm the wildness of Earth's tilt. The tides still rise because of a relationship born in impact. Even eclipses, those brief hushes of the sky that still make crowds stop and stare, are a lingering consequence of the ancient geometry between these two bodies. When you look up at the moon now, it is easy to think of it as permanent, serene, almost detached from the troubled young Earth. But it is not detached at all. It is part of Earth's oldest memory. It is the visible reminder that our planet was not formed once in a simple event and then left alone. It was assembled, melted, struck, reshaped, cooled, flooded, and accompanied. The moon is not just nearby. It is family in the deepest planetary sense, made from the same beginning, bound by the same old violence, still present through every tide and every night. And that may be why this story feels so grand and so intimate at the same time. It begins with stars and dust and giant impacts, things so vast they seem almost beyond emotion. Yet the result is the ordinary world around you. Stone paths, river mouths, cloudy evenings, wet sand under moonlight, the slow pull of tides on a shoreline, the fact that there is even a shoreline at all. These quiet things were not guaranteed. They were earned by a long chain of events so unlikely and so precise that the mind can only sit back and admire how much had to happen for Earth to become this Earth. A rocky planet had to form in the right region around the sun. It had to grow large enough to keep an atmosphere and sustain internal heat. It had to differentiate into layers. It had to receive water and keep it. It had to survive a giant impact without being destroyed. That impact had to produce a moon of the right kind. The moon had to remain bound and then drift outward at the pace it did. The bombardment had to ease. The crust had to stabilize. The oceans had to persist. Chemistry had to go from interesting to alive. And through all of it, the Earth kept going. That is the feeling to carry with you at the end of the journey. Not just awe, though there is plenty of that. Not just mystery, though the story still holds many unsolved corners. Something gentler. The sense that the world beneath you is ancient in a way that is almost loving, not because it was made for you, but because it survived enough to make room for you. The ground did not always know how to be solid. The sky did not always know how to carry rain. The moon was not always there. But they came into being together, and together they made the long road toward home. So when you imagine the Earth and Moon now, drifting through the dark in their old partnership, you are really seeing the afterglow of formation, a cooled remnant of fire, a stable rhythm rescued from chaos, a night sky carrying the scar of Earth's beginning in the most beautiful way possible. And somewhere in that thought, the story softens. The early fire dims. The impacts grow distant. The oceans grow still. The moon climbs quietly, no longer newborn, no longer close enough to fill half the sky, but still near enough to silver the water and keep its ancient hand on the tides. You can let the vastness rest around you now. You can let the deep time settle. You can let the planet be old and steady and carrying you without effort. You can let the sky be wide above it. And you can remember that before this world was gentle, it was brave. The darkness of space no longer feels empty. It feels patient. The stars seem less like cold points and more like witnesses. Earth turns beneath them with the calm of a world that has already survived its most violent beginnings. The moon follows, faithful and pale, shaped by the same history, keeping the same face turned toward home. The seas answer in their sleep-soft rhythm. The air moves lightly above the land. The long machinery of the planet hums on without asking anything from you tonight. So you can rest inside that rhythm. You can feel how old the ground is beneath every ordinary day. You can feel how much fire had to cool, how much stone had to gather, how much rain had to fall, how much time had to pass before there could be quiet. And in that quiet, the story finally becomes simple. A world was formed. A moon was born. They stayed together. And somehow, after all that chaos, there was room for stillness.